energy. For electronic transitions, especially at the frontier orbitals or at the valence bands of your material, you need to be using visible light or ultraviolet light. For X-rays, we can also probe the sort of electronic transitions, but that's not really what we can do here. The bigger thing for us is that when you get to X-rays of the appropriate energy, the wavelength of those X-rays are on the same order of magnitude as interatomic distances inside of our molecules and materials. So this is a good probe that helps us look at structural information for the materials that we're growing. And so to sort of explain how we're able to take our X-ray diffraction patterns and convert them back into useful structural information, I'm just going to briefly walk you through Bragg's law, which is a simple way of thinking about how X-rays interact with your material. So here I just have our two-dimensional crystals. So it's these planes of atoms that are separated by a distance d. And if we shine X-rays down onto our sample, the X-rays will interact with the electrons in our atoms, and then they'll be scattered away. And so, as you see, if you have two different layers in your material, there's a path difference for the X-rays to travel between those two layers. So that means as the X-rays are leaving our sample, there's going to be a path difference, and so they're going to be subject to interference. And so obviously if we're trying to get a signal out, we want to make it so this path difference here matches up with the wavelength of our X-rays. So we want it to be some integer multiplied by the wavelength of our X-rays. And luckily, because of this construction, we can do some simple geometry, and we can show that the angle that the X-rays are incident on our sample, theta, is also this angle here. And half of our path difference then is equal to d sine theta, which means that the total path difference is 2d sine theta. And so this is Bragg's law. This gives us a very simple relationship between the planes of atoms in our sample, the wavelength of X-rays that we're using, and the angle that we can actually control in our experiment. Just to note as we continue, most of the time in experiments, we don't measure theta, we measure 2 theta, so don't be tripped up by that as we go along. And so using this basic principle, we can do fairly complicated experiments. So if we have grown a single crystal of our material, if we take that crystal and we shine X-rays on it, twist it every way that we can think of, get as many different diffraction spots as we can basically look at all of the planes of atoms that are present in our material. This is a crude cartoon just to show you what the experiment looks like if we sat and watched it. Over here is some actual data that was collected on a sample here in the arc. And so these are very typical images that you see. You see a bunch of spots, and as we rotate the crystal, the spots change and new ones appear. And the beautiful thing about the experiment is we can then take all of that information. We can arrange all those spots, and we get information about all the distances in our crystal. And then we can convert that into an electron density map, and we can figure out where all of the atoms are in our material. So if we have a compound, we don't know what it's made of, we can figure out what it's made of using this technique. Now, for those of you that haven't grown single crystals before, it is hard. It is a difficult thing to do. So more likely, you're going to be working with powder samples, which the way to think about powder samples is they're just a bunch of crystals that are all randomly oriented relative to each other. And so the way to think about how that would appear in an X-ray experiment, if we take one of the frames of our single crystal data and we just highlight one of the spots, if we then imagine we take an exact copy of that crystal and just rotate it a little bit, and we keep doing this, you can see that we're getting sort of a circular pattern for how the spots move in the material when you start to randomly orient a bunch of these crystals together. And indeed, if you have a randomly oriented powder, instead of seeing those individual spots like you were seeing before, you're going to see these powder rings. And so because we are looking at rings, they are the same everywhere. For simple experiments, it's easier just to sort of look at a single line. So rather than moving your sample all over the place, we're just going to trace sort of a line in space and take a cut of those circles. And that can be transformed into the sort of typical diffraction image that you see here, where each spike on this image represents a particular plane in your material. And for any given material, this pattern is going to be a fingerprint. So this allows us to do things like if we have more complex samples, we can go through and we can pick out multiple things that are present in that sample, and we can quantify how much of each thing is present. So applications, what can we use X-ray diffraction for? And I've been talking about this a little subtly, but I've been using the word crystal and crystalline and crystallite. And that's because X-ray diffraction relies on the fact that there needs to be long-range order so that we can build up lots of these interference events to get a signal. So unfortunately, if you work with materials that are not very crystalline or don't have long-range order, these techniques are not going to be as useful to you. But if you're crystalline, then X-ray diffraction is definitely something you might want to look into. And so thinking of powder samples, you can identify compounds that are present in a sample, and you can quantify the amount. If you're synthesizing a new material, you can check for any impurities that are left over from your synthesis. You can examine the size of the particles that are present in your sample and calculate strain in those particles. And also, if you have a very good sample and very good data, you can determine a structure directly from powder. You usually need high resolution data to do that. If you happen to be making thin films, again, you can do phase identification and you can check for impurities. For thin films, it's also nice to be able to check for strain or texture just to see how well that you laid down your thin film. It is a thin film. You will likely care about how thick it is. You can measure the layer thickness directly using X-ray diffraction techniques. And in the case of if you're trying to get a specific layer of atoms to be present on the surface of your film, you can also check the orientation of that film so you know which way things are pointed in that film. And finally, single crystal. The main thing that you do with single crystals is that you want to know unknown structures, or you want to understand structural changes as you go through phase changes or dope or alloy things into a material. If you can grow single crystals of it, you can try to track where atoms are ending up and get information about your material's properties that way. And again, on top of all the things that I've already discussed, you can combine these techniques with variable temperature. You can do it under different atmospheres to try to monitor reactions in situ. You can put your sample between two diamonds and press it to pressures above what you would experience in the center of the Earth. You can also do time-resolved experiments as well, if you have the correct setups to do that. So with that, we'll talk about what the ARC can do specifically for you. We currently have 3 instruments that are in operation to do X-ray diffraction. We're going to start by talking about the instrument we've nicknamed the PXRD, the Powder X-ray Diffractometer. This instrument is great for routine analysis. It's definitely the workhorse of the X-ray lab. It's constantly being used. This instrument is set up for powders and thin films, but mostly for doing a lot of things with powder samples. The way that the X-rays are focused, they're line focused, so that means it's best for doing the type of example that we talked about when doing Bragg's law, where the incident and diffracted beams are sort of looked at symmetrically. The main stage for this instrument that's almost always installed is called the flip stick. It's a 9-slot sample changer that allows you to load up to 9 samples and walk away to do other work while your samples are running. Each of those sample slots, you can spin the sample to help it appear more random to the X-rays. There's also an anti-scatter blade to help you cut down on background if that's an issue for your samples. We also have the ability to put in a silicon zero background holder. So if you really need to eliminate background, we can get rid of it. And if you have air sensitive samples, we also have ways of packing your sample so that it is protected from air and moisture if necessary. This instrument can also be operated in either a reflectance or a transmission mode. So if you need to, you can send the X-rays through your sample and get a diffraction pattern as well. That is also compatible with this sample changer. You can couple this with our biologic electrochemical cell, so you can try to run electrochemical reactions in situ on your materials if you wish. We don't get a ton of call for that stage right now, so if anybody's interested, please let me know. The other big stage for this instrument is our variable temperature stage. So this stage only does heating, but it can go from room temperature up to 1200 C with heating rates of up to 60 Celsius per minute. The stage can be operated in air or vacuum. There's two ways that you can mount samples. There's a corundum stage where you can put powders or thin films down as long as the thin films are small enough. Again, you can rotate samples. There are anti-scatter shields if you need them. The other way that you can use this sample stage is you can also fill a capillary with powder and you can place it into the instrument to do transmission measurements if you like. There's not a lot of call. There hasn't been a lot of call for this stage recently, so it's on a request sort of system. So if you're at all interested in using this stage, you can send me an email. We'll block out time for this to be installed. If it gets used more and more frequently, we can also change the schedule to work it so that this can be mounted on a more regular basis. So that's the powder system. So moving on to our other diffractometer, which is referred to as the thin film XRD, and is therefore, unsurprisingly, optimized for analyzing thin films. And particularly the main thing that it's useful for is doing grazing incidence X-ray diffraction. So the optics on this system, the X-rays are adjusted so that the beam is parallel rather than line focused. And the incident angle is extremely shallow so that the X-rays aren't penetrating very far into your sample, so you're mostly seeing diffraction from your surface, hence why it's more useful for thin films. It's also got a quarter circle Tellurian cradle installed, which allows you to manipulate your sample very easily in space. So it has XYZ motors to help you align your sample, and then it can also rotate in what's called the angle phi, which is just rotating your sample like on the powder X-ray diffraction instrument. But importantly, you can also rotate your sample on this stage in chi, which means that you can tilt it. So if you have a thin film where, let's say, it's oriented in a very particular direction, because you can tilt along chi and phi, you can actually map out all of the diffraction spots in space that you normally wouldn't be able to see by doing a normal 2 theta scan, like we talked about for the PXRD instrument. And for this stage, again, because it's meant for thin films, there's a vacuum suction stage to attach your substrate to this holder. Because of the way this instrument is set up, it's also very good for measuring texture on your film, so you can help see how well your film has been put down by looking at the full width of half max of all your peaks. So if you're interested in strain or texture, this is a good instrument to use. In addition to stress and strain analysis, you can also adjust this instrument to work to do X-ray reflection. So you basically, to do X-ray reflection, you're going to decrease your incident angle to the point that you pass a critical angle, and now you get total reflection of all the X-rays. And this technique is very useful for getting film thickness information because you're literally watching the X-rays sort of interfere with the surface, and there will be a pattern that depends on the thickness of the film that you made. It is also possible to switch this instrument over from the parallel beam optics to do a line focused option. So you can do XRD. There's also a monochromator for this instrument, so you can filter out the X-rays so that you only have essentially one wavelength available if you need higher resolution data. Okay, and then the last instrument we're going to talk about is the single crystal instrument over in ChemR. Its job is to figure out crystal structures. That's sort of the main thing that it can do. Of note for this instrument, unlike the other instruments that we have for X-ray diffraction, it doesn't use a copper tube, it uses molybdenum radiation, which molybdenum is higher energy, so it's more penetrating. It also allows you to have much higher resolution for your single crystal data sets, with the drawback being that because it is higher penetrating, it's better for samples that have heavy elements present within your sample. So things that are mostly carbon are going to be a little bit harder to work with, but it works just fine. And if you need help, reach out. I can help you figure out how to set up the experiment. This system is equipped with an Oxford cryostream, so we can adjust the temperature of your sample from 80 to 400 Kelvin. And because it uses liquid nitrogen as the way that it does this cooling, that also means that it inherently can protect air-sensitive samples and exclude oxygen and water from those samples when you're doing the experiment. Keep in mind, if you're working with these single crystal samples, we're aiming for something on the order of 20 to 300 microns. If it is bigger or smaller than that, this instrument is going to struggle with working with that type of sample. So just be aware of that. Another thing that this instrument can do is it can, in principle, also do powder X-ray diffraction if you want to. The powder will have to be mounted in a capillary to do it. And because we have the cryostream, we can cool samples. The drawback here is, again, because we're using molybdenum radiation. If we think back to Bragg's law, if we increase the energy of the X-ray, decrease the wavelength, it means all of our angles are going to be much closer together. So you might lose resolution in 2 theta versus a copper system. So it's something to be aware of if you're interested in doing that sort of experiment. The last thing that I'm going to talk about, I suppose we can consider this an instrument, is the XRD workstation. This is a dedicated computer that is in the ARC that is meant for working up and examining your X-ray diffraction data so that you don't have to sit at the instrument computer to do any workup. This is free to use for anybody. You just have to come talk to me. I'll show you where it is and how to log in, and you can start working with that system. I've loaded a bunch of software onto that system. It has all of the software that's used by the instruments to collect data and analyze data. There are also additionally some extra programs to help you work up your data, to visualize it, to make figures if you like. And we've also incorporated onto that instrument a variety of databases that you can compare your data against. And so I would like to take a brief diversion and talk about these a little bit, just to make sure everybody's aware that these are available and that they are very useful. Even if you're not doing X-ray diffraction, it's a great way of hunting down sources when you're doing literature reviews as part of your research. So the main one that I'll start with is the Cambridge Structural Database. This is a massive database of organic and metal organic crystal structures. It is very easy to search and analyze these structures and work with. If you are on CSU's network anywhere, so this doesn't have to be in the ARC, if you search for WebCSD, you will come to a page that gives you access to all of the structures this database has. So you can search the database using a publication that you know of, authors you're interested in. You have a search where you can put in a specific structural motif you want to look for. And it'll return every entry that vaguely matches the parameters that you put in. And then you can also download all of these crystallographic info files or CIFs so that you can examine them using whatever software you prefer. So In addition to having this website that you have access to, there's also a variety of programs that are loaded on the workstation computer that you can use. The main one that I use a lot is Mercury, which lets you take SIFs and you can visualize the structure and do analysis. You can measure whatever properties you like using this. You can also do searches of the database through Mercury and data mine. You can study crystal structures to look at the differences in their polymorphs. You can look at the properties when you scale it up to particle size. You can look for various intermolecular interactions if that's something you're interested in. You can also prepare figures for publication, or if you want, files for 3D printers to read out. Other programs are things like Encipher, which lets you open up SIFs and edit them, which is mostly useful for if you're preparing a publication or need to extract any information out of a SIF. For people that care more about macromolecules than small molecules, there's a program called Hermes that lets you visualize and analyze macromolecules and proteins. And it's integrated with another program called Gold that will allow you to do protein ligand docking studies, if that's something you're interested in. And then in addition to this program also comes with a Python API. So if you want to customize any scripts or workflows, you can do that as well. And again, all of these programs are accessible on the workstation. In a similar vein, there's the Inorganic Crystal Structure Database, which is sort of the inorganic counterpart to the CSD. You can search it very easily as well. Pull crystal structures much as the same way I talked about the CSD. And then the last one is the powder diffraction database, which has simulated powder data and actual powder data for over 1 million different compounds. This is integrated into our software that works with our PXRD, so you can go through, use this database to do phase identification to help you with quantification. It's also a good way where if you search for specific types of materials, everything's tied back to publications as well, so you can also do literature searches this way. In addition, I'd also just like to mention that I am working on developing various tutorials or cookbooks for various techniques. So hopefully those will be coming soon and you'll be able to access those as well on the workstation. And finally, I've also started compiling a lot of webinars and other learning resources onto the ARC Xray Teams channel. So please check out there if you're looking for any help or tutorials on anything you might be interested in. And then the last resource, if you want to think of me that way, is me. I can help you with not only your experiments here in the ARC, but I also, from the research that I've done, have made connections that can help you get access to other experimental techniques that you would be interested in. So, for example, unfortunately, our SAX instrument has been having more problems recently. So I will be able to direct you to Boulder to do any sort of SAX experiments that you're interested in. So this is useful for people that work with polymers or macromolecules who are interested in looking at large features that might be present in your materials. I've also worked a lot at various synchrotrons and beamlines around the country. So if you have a small molecule that is very difficult and it's hard for us to collect here, I can connect you with people at synchrotrons that can really hit it with very intense X-rays and help you get the structure. I can help connect you to people to do high-resolution powder data, get high-resolution powder data, connect you with people to do other X-ray techniques like absorption experiments, or time-resolved work or high-pressure work as well. And then as Caroline mentioned, I've used a lot of XRD throughout my research, but I think the thing that I enjoy the most is doing single crystal work. So if you're interested at all in single crystal XRD, I can help you with crystallization techniques if you're ever having trouble crystallizing your material that you're interested in. I can help you walk you through routine crystal structure solution if that's a problem you're having, or if you're running into issues with disorder or twinning or modulated structures, which just to cover very briefly. So I've been approached to do a couple of crystal structures since I've been here. And already it seems like a common thing that comes up is disorder. So here, for example, is a molecule where it has CF3 groups, and CF3 groups are very notorious for liking to disorder. And by disorder in this case, I mean that there are multiple positions in the crystal structure where that CF3 group can sit. And so when you're trying to solve the structure, you just get sort of a cloud of electron density, and it's kind of annoying to pinpoint where the atoms are in those structures. So I can help you resolve those problems, even if it's disorder like this, or if you have something where, say, at one position in the crystal, a molecule can sit in multiple positions. So you end up with something like this, where you have what looks like two thiophene rings that are intersecting each other. I can help you resolve issues like that. Or if your molecule crystallizes with some solvent, they tend to be disordered and are sort of hard to wrangle. I can help you with that as well. We'll skip through some of this. I can also help you deal with twinning. So if your crystal decides partway through its crystal growth that it's going to change direction on you, and now it looks like you have more than one crystal, it is harder to solve because you have two crystals now, so there are spots that overlap. I can help walk you through the process of figuring out where your two phases are and separate them out so that you can get a good solution. And then the last thing I mentioned was modulated crystals. So it is possible for atoms to periodically vary in their position as you move through the crystal structure. And it leads to odd things like your Bragg peaks being split into multiplets, which here is an example of what that looks like, where each of these is not a Bragg peak itself, but is a satellite of the main Bragg peak. So if you run into any of these problems or other problems that I haven't mentioned here, I'm very willing to help you. And if we don't have access to something in the ARC, I want to help you get access to it. So please reach out if you have any questions. And I think with that, I will stop and open it up for questions. Thank you for your time.
Any questions for Ethan? You can also post them in the chat. That's easier. Great presentation, Ethan.
Thank you.
Now's your chance.
Hi, Ethan, that was a wonderful presentation, really informative. I had a question on single crystal. Do you know kind of the time frame to collect a data set, like how many hours it would take?
It is highly variable. If you are working with, okay, so the time will depend sort of on the symmetry of your crystal. Ballpark, it can take anywhere from 4, 5, 6 hours up to 30. It purely depends on how well your structure is crystallized, if you have heavy atoms, and if your crystal has a lot of symmetry elements, because the more symmetry it has, the less data we have to collect. So if you want to reach out to me and talk about a very specific system, I can probably narrow that window down for you. But yeah, the time scale is on the order of multiple hours to days.
Okay. Yeah. I appreciate it, and I will absolutely reach out.
Mm-hmm. Anything else?
Ethan, can you talk a little bit about some of the efforts around bringing a more advanced single crystal in the ARC?
Yes, I would love to. Yeah, so our single crystal instrument, there's nothing wrong with it. It works great. But, oh, it's way back here, isn't it? There it is. But we would love to add some more capabilities. As I mentioned, currently the only operating single crystal instrument we have uses molybdenum radiation, which for those of you that work with organic molecules, this is definitely usable, but not ideal. Ideally, you would have copper. So what we're hoping to do is, with Jamie Nielsen and I, we're trying to put in an NSF MRI to get a newer system that would have both copper and molybdenum, so it would be useful for all types of samples. And we would have in that system a very large and powerful new generation of detector that's extremely sensitive. I worked with an instrument like this when I was at Duke, and crystal structures that would have taken me like 10, 12 hours on older systems that I had used took like 30 minutes with that new system. So it's a very powerful tool. And I believe Jamie also wants to set that up so that it can also look at the diffuse scattering around your Bragg peaks so that you can pull out additional information as well. So yeah, hopefully we can get funding for that instrument and really upgrade capabilities and move some crystals through a little faster. But yeah, so I think that's the current plans that we have. And I guess this is also a good time while we're talking about single crystal to plug that working with Roy, we're also trying to add electron diffraction to our services as well. And so rather than using X-rays, you use electrons to do the diffraction experiment. And this is done inside of the TEM. So this would be very useful for people that have difficulty growing large single crystals. So rather than needing something on the order of microns, something on the order of hundreds of nanometers can be used to do diffraction as well. So we're working to get that capability set up as well, so that we can help out those that have systems that just don't like crystallizing, like proteins or certain inorganic materials that have trouble crystallizing.
Hi, Ethan. I had a quick question for you. I was just curious, what's the process for reserving time on one of these instruments, and how long of a block do we need to book for if I'm doing powder XRD, you say?
Yeah. So all of the instruments are controlled through iLab. So there are schedules in iLab. There's a schedule tab. You can find each individual instrument. Once you are trained on an instrument, you'll have access to the calendar and you can block out time. For PXRD, we request a minimum of a half hour. In fact, I think iLab will force you to take at least a half hour.
Okay.
And then there's no set upper limit. I think the longest I've seen is people will measure things for 3 hours at most if they're running multiple samples. So that's a pretty typical time frame, and that's sort of the process.
And you said we have to get training first. So
correct.
What's the process for getting that set up?
Yeah. So once you're all set up in iLab, you can send me a training request via iLab, and then we'll schedule time to meet after you complete your X-ray safety training. And then I will show you how to use the instrument. I will activate the calendar for you in iLab, and then you're set up to do whatever you need to do.
Okay, great. Thank you.
Mm-hmm.